Problem 2. A cart with mass 340 grams moving along a frictionless linear air track at an initial speed of 1.2 meters per second undergoes an elastic collision with an initial stationary cart of unknown mass. After the collision, the first cart continues in its original direction at 0.66 meters per second, while the second moves at 1.9 meters a second. A. Is momentum conserved or not? Explain. What type of diagram is appropriate for this situation? An impulse momentum or momentum bar diagram? Draw it. What is the mass of the second cart? A. Draw a picture of the situation along with a bar diagram. So when I look at the situation beforehand, I have a block that's coming in, and I'm going to say that it comes in with some initial speed. And there's a second block that's stationary. And this has a speed of 0, so it's initially at rest. So in other words, I'm going to call this block 1, and I'm going to call this block 2. Now, what we know about the impulse momentum theorem is that if there's an impulse, and when we talk about the net impulse, it's the impulse due to the external plus the impulse due to the internal, that this has the ability to change the momentum. So I have to define my system. So what is my system to see what's going on? I know that this is occurring along a frictionless surface. So if I go here and I make my system here, it's going to be block 1 plus block 2. So now if I look at this thing, I could then say that there are no external forces. That can change momentum. Now note, we only care about the horizontal forces because the velocities are in that direction. So in this case, because it's frictionless, that implies then that F external is equal to 0, which then tells us that the external impulse is equal to 0. So now, what about internal forces? Do they change momentum? And what we find here is that because we included both carts into our system, Newton's third law implies that the internal forces are going to be two of them. There's the force of one acting on two, and then the force of two acting on one. But according to Newton's third law, this is equal and opposite to the incoming force. So in other words, I get that F12 minus F12 is 0. So then this tells us here that the internal impulse is also 0. So then from the impulse momentum theorem, I have no external impulses, and the internal impulse, this is actually 0. From Newton's third law, this is 0. So therefore, the change in momentum has to be 0, which then implies that the momentum before and the momentum afterwards are exactly the same. So in this case, we then say momentum is conserved. So now that I know momentum is conserved, I could then say that if I look at my bar diagram, so if I take my picture from before and I bring it down here, I could then say that then after the collision, listening to their words, they say that block one, right? Let me copy this. Continues to move forward. Okay, this is going to be afterwards. This guy continues to move forward, and block two now also moves forward. So then my bar diagram looks like what here? So my bar diagram is a momentum one. And what it says here is that I have this amount of momentum coming in. And that momentum is going to the right. And all of that momentum is contained within block one. The momentum of block two is 0. So therefore, the total momentum of the system cannot change. That has to be a constant, which is equal to P total. Afterwards, because momentum of one continues to go forward, I would expect that most of the momentum stays with block one going forward, and some of the momentum is transferred to block two in order to have this situation right here. So then, because of this, we can then say that conservation of momentum says that P1 initial plus P2 initial must equal P1 final plus P2 final, but we know here that this guy starts off at 0. So if I write out more of the details of this, this will then be M1 V1 initial equals M1 V1 final plus M2 V2 final. Well, now, if I go to B, now that I have a picture of the overall situation, I can, so to determine the mass of the second cart, M2, we isolate M2. So if I isolate M2, you could see here that I need to isolate M2. So I'm going to start with the process where I'm going to isolate MV2 final, and then I'm going to bring M1 V1 final to the other side. So this will be M1 V1 initial minus M1 V1 final. Then I'm going to isolate the mass. And now I can divide. So in other words, this is telling me here that if I now isolate M2, M2 is then going to read M1, V1 initial, V1 final, divided by V2 final. So then the numbers given in the problem read something like this. We know that M1 is going to be 0.34 kilograms. Its initial speed is V1 initial. They tell us that it's 1.2 meters going to the right. Afterwards, it continues going to the right at a lower speed. And then cart 2 moves off at 1.6 meters per second. So if I plug in my numbers, I'm going to get that this is 0.34 kilograms times the quantity 1.20 minus 0.66 meters per second. And I'm going to divide this into 1.9 meters a second. And unit-wise, you could see that these guys immediately cancel. And when you plug this into your calculator, you get 0.097 kilograms, which is the mass of 2.